The dynamics of free relativistic particle of mass m is governed by the Dirac-Hamiltonian H equal to C alpha dot P plus beta mc square. Alpha and betas are 4 cross 4 matrices. P is the momentum, m is the mass of the particle, C is the velocity of the light. Where P is a momentum operator, alpha is alpha x, alpha y, alpha z, and beta are 4 cross 4 Dirac matrices. The acceleration operator can be expressed as, what is the acceleration operator they are asking. This is a big derivation already I have done. I want to explain what I have done. Before finding the acceleration operator, we want to know what is the velocity operator. Already from the Heisenberg equation of motion, we know that any operator derivative, suppose position operator derivative dx by dt should be equal to I h comma, it will come out commutation h comma xi. What are the operators if you are taking derivative? That commutation with the Hamiltonian into I h hat. So this equation we know from the Heisenberg equation of motion. Dx psi by dt is nothing but velocity. Just to substitute the Dirac Hamiltonian here. C into alpha dot b plus b alpha dot b plus beta mc square comma x. Use the commutation rule. C into alpha I dot pi. I am writing that in terms of Einstein notations. Alpha I dot pi comma xi. These are the vector. Each I represents each and every component here. If it is 3-dimensional, it will take x1, x2, x3. Same p1, p2, p3. Alpha I also, alpha x, alpha y, alpha z. It will take the 3-dimension. Plus beta mc square computation with xi. Beta mc square with the position operator, anything with the position operator, it will come at PS position operator, not a derivative operator, it will come out with any other quantity. So this commutation goes to 0. Come to the first commutations. C alpha I, the momentum operator I am writing dou by dou xi minus I h I am taking out, comma xi. We can cancel this sketch cut, I into I square minus 1, already 1 minus, plus. So C alpha I dou by dou xi comma xi. Operate with the wave function on both sides, then only the commutation will give the right answer. So if you are operating on right hand side, first this minus this into this acting on psi, so minus of xi into C alpha I dou by dou xi alpha I dou by dou xi acting on psi. Dou by dou xi acting on these two quantity. First keep the psi outside, it will act on the xi, plus C into alpha I, it is a constant, you got to keep it left hand side. Now keep the xi outside, dou x by dou xi acting on psi, minus this quantity. If you see this equal to this, we can cancel these two. So the final answer is velocity operator equal to C into alpha I, because dou xi by dou xi is equal to 1. If you are removing psi on both sides, the velocity operator will give C into alpha I. For finding the acceleration operator, we are going to use this result. Acceleration operator for the Dirac field A cap equal to I h theta by h comma commutation of velocity operator, commutation with the h. That means suppose if you are writing Heisenberg equation dv by dt equal to I h cut h commutation with the velocity operator. This left hand side is acceleration operator, I am writing here. Then right hand side is velocity commutation with the h, I am writing here. We can substitute the Hamiltonian here. Before that, I want to modify the given equation. Instead of vector quantity, I am writing the component form, the Einstein notation form. Here also, left hand side also, the acceleration operator, we are writing the notation form. I by h cut, first expand this commutation. Hi vi minus of vi hi. This is the expansion of the commutation relation. I am adding and subtracting one more term, that is minus VIHI plus VIHI. Now if you see these two terms, this will form, this both are same terms, so minus 2 VIHI plus other two terms will form the anti-commutation. Anti-commutation relation already we know, so HI comma VI anti-commutator. This bracket represents anti-commutator of these two. So this term will form the anti-commutation. Minus 2I VI as it is. Now we will substitute our Hamiltonian, Dirac Hamiltonian, that is C alpha I PI plus beta M C square comma VI. So minus 2 VI HI plus expand this anti-commutations. So the first anti-commutation is C alpha I PI anti-commutation with the velocity operator. Then next plus beta M. The first commutation C alpha I PI anti-commutation with VI. Then next plus beta MC square anti-commutation with VI. The first term as it is minus 2 VIHI plus the anti-commutation expansion of these two C alpha I PI VI plus because it's anti-commutation VI into C alpha I PI. C is constant, I am taken out, plus if you see these terms, this is Dirac matrix, this is also Dirac matrix because VI already previous expression we found VI equal to C into alpha I, the velocity operator for the Dirac Hamilton field. Velocity operator is equal to C into alpha I. So this is also Dirac matrix, this is also Dirac matrix. Two Dirac matrices, D1 Dirac matrix will anti-commute with each other is equal to 0. Anti-commutation means it is that value is equal to 0. So this last part goes to 0. This last anti-commutations. Now we can consider these three terms. Write this term, write this term, write this term as it is. Now come here. I by h cut substitute the velocity operator of the Dirac field minus 2. The velocity of the operator for the Dirac field C into alpha I hi plus C square alpha I square into Pi, because Pi and alpha I will come to each other, so we can rotate these two, plus C square alpha I square Pi. Now come here, take the 2 out, C also out, already I is there h cut. If you see this term, first we can see this term. Alpha square, we know the Dirac matrices square is always identity. So unit matrix, this will become unit matrix, this will become unit matrix. So this is 2 times, that's why we are taking 2 out. 2 times, already 1 C out, so C into Pi. If you are taking 2 out, C out minus alpha I hi. In the vector notation, A vector equal to 2 IC divided by h cut C P minus alpha h. So the right option is 1.